Hi folks, this is a very simple trust analysis that I will be doing with the Explicit Dynamics feature available in the 3D Experiences FEA solver. Keep in mind that the FEA solver in the 3D Experience is actually the ABAQUS program. Now, this being part of the transition series, what I do is I find uh, problems such as this that are done in its entirety using the ABAQUS CAE program and are available on YouTube, and replicate the steps to show you the differences between the interface and some of the functionalities. For all practical purposes, the difference is in the interface, because for functionality, it's the ABAQUS CAE program, but there are certain things that are not completely integrated in the 3D experience yet. It's a simple truss structure like that, and the load here is applied to that node, 600 Newton over a very short duration. So we're going to solve this thing as a dynamic problem. The cross-sectional members have a radius of 2 centimeter. That incidentally, 2 centimeter uh, is going to translate into 2 pi times 2 squared, or 0.02 squared. So, uh, sorry, not 2 pi, pi r squared. So pi times 0.02 squared. Okay. Uh, that is, yeah, that is meter squared. All right. So let's go ahead and do this. Come back to the comparison later on. So here is the 3D Experiences interface. So we go to the part design. I'm going to create several points in space and then connect them with lines to mesh it into beam elements, basically. There are easier ways of doing it. This entire uh, shape can be done in a sketch, but I rather not do it because there are certain things that are going to pop up that it's good to notice. So let's see now. We're going to create 1, 3, 4, 5, 6, 7 nodes. Okay, 7 points. So let's go to Essentials. Let's start at the bottom left corner. So 0, 0, 0 is good. Units are in millimeter. And then the next one to the right of it is going to be 2000 millimeter to the right. That's going to be 2000. Next one is going to be 4000. 4000. Then we go and do the ones on the top. So if you go back to 0 here, 2000 in the vertical direction. There we are. Then it's going to be 2000 and 2000. So that's this point. And then it's going to be 4000 and 2000. And the last point, point number 7, is going to be 6000 and 2000. And we're done. So we cancel that. These are the points. Now we're going to create the lines. A line from here to here. Another line from here to there. Okay, one from here to here. From there to there. These eventually are going to be our beam elements, or truss elements, actually. As I said, there's a much easier way of doing these things with the sketches. Instead, I'm doing it basically point by point and line by line. Done here. So what you see there is actually this configuration. And now uh, there are different ways of doing this thing. I can, for example, join these lines and mesh the whole thing, or mesh them one by one. That's entirely up to you. So to make my job harder, I'm not going to join them. Okay, I'm going to do mesh them one by one. You see why in a second. All right, so this is the stuff. And now I'm going to create a material. This is steel, January 21, 2024. Okay, going to be created right there, and then I'm going to apply. I don't need this. I'm going to apply to that, and then we input the values. So we go here. It's a structural. We need a density, so I'm going to put the density in there, which is 7,800. 7,800 kilogram per meter cube. That's the standard density for steel. And then ABAQUS multiphysics, mechanical, elasticity, elastic, 200 gigapascal, 200 GPa. Okay, and Poisson ratio 0.3. Although this Poisson ratio is not used, but we're going to input it anyway. Good. Let me do a quick save here. Now I'm going to do a meshing. Okay, so we go to the structure model creation, MTFEM. Okay, and then for mesh, beam elements. Now I'm going to do this thing one by one, because if I had joined these things, I could have taken the whole thing, but I decided not to, and there was a reason that I'm going to do that. It's going to be longer, but there's a reason I want to do this. So select this and mesh it. And the size of the mesh, I put down 3,000, so that I guarantee that there's only one element created here. I could have done 2,000, it doesn't matter, because this is, 3,000, because this length is roughly 2,800 millimeters square. Millimeter, not millimeter square, 2,800 millimeter. By making 30,000, it guarantees that there's going to be one element through all of these. Now, I want to do the other one. Okay, the other one meaning this. Now, the problem is that because I did not join these things, there is going to be duplicate nodes at this location. So what I can do is that I can say that capture the nodes that are within 10 millimeters of each other. Okay. You can change this thing, as long as guarantee that there's a single node here. It doesn't matter. I put down 10. Any two nodes which are within 10 millimeters of each other are going to be merged, essentially. Now, keep in mind that these two nodes are going to be on top of each other, so actually they are within 10 millimeter tolerance. So mesh, okay, and do it again. If I had joined these things, don't forget again, same thing. If I had joined these things, this would not be required. Oh, did I mesh this one? Let me see. Let's do update, make sure everything's okay. So these are all meshed. So let's go to the other ones. That one, mesh. This one, mesh. I know it's crazy, but I wanted to show you some of these features, some of these things that you have to worry about if you don't merge. Okay, another one here. And finally, that one. I don't think I did the last one. Update. Good. So there should be 7 of these. No, let's see now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are the ones. Now, how do we know actually it worked? So if I go to display, by the way, let me hide all these points. It is important to hide these points because later on, when we restrain points or put a load on it, we don't want to put it on point. We want to put it at the vertices. So let me hide all these points. Good. Okay, so we go here. We go to display a numbering visualization. You click on it. All right. So note, if I put my cursor there, it's going to give you node number 1, node number 2. If I go on this side, node number 2. If I go from this one, node number 2. So it has merged the nodes at those things. If I had not asked for that, then there will be duplicate nodes here. Let me see now. Yep, duplicate nodes here, it'll cause a problem. So that's good. All right, so now the cross-section. So we go to properties. Under these are not beam, they're links essentially, 1D links. Okay, so Truss members. You click on it. Okay, so can I use all of them? Yeah, one by one. So 1, 2, 3. Make sure I don't miss anything. Okay, and what is the area? Now the area is pi times radius squared. Radius is 2 centimeter, so it's going to be 0.02 centimeters. So what I can do, 0.02 meters. So what I can do is do the following. Pi is 3.14 roughly times radius squared. The radius we were told it is right here, 2 centimeter. So it's going to be 0.02 times 0.02 or 0.02 squared. So this is of course going to be meters, meter squared. Okay, so I would have thought that it would take something like that. It didn't, so let's do the following. Let's go put the right there. So see now, so that's going to be point pi times times 4 divided by 1,000 or 10,000. 4 pi is 4 times 3.14, so that is 12.56. Yeah, times 10 to the minus 4. Okay, let's try this way. I'm surprised that it didn't take the other one, but 12.56 e to the minus 4 meters squared. Okay. And notice that it actually shows you this a configuration that shows you these are represented by those truss members. Now keep in mind that when you do trusses, the cross section of area is important. It doesn't have to be circle. However, when it comes to displaying it on the screen, you can it's going to look like a circle. Okay, let's update this. Good. We are done here. So now we're going to go to let's see if we can actually, let me see for a second if I can get rid of that's okay. We will get rid of these. I mean, obviously, if you don't want to see that, you can hide it. I was trying to do it a different way. Okay, let's go to the structural Because we're doing explicit analysis, you cannot go to structural scenario creation. You have to go to mechanical scenario creation. This does not have the explicit solver in it, but this one does. You click on it. All right. So we are doing the finite element model has been created, and we are doing a structural one, and we say okay. And now on the procedures, we're going to do explicit dynamics. So this is implicit dynamic, this is explicit dynamics. Okay, the total time step is 0.01. Okay, and of course, by default, nonlinear geometric effect is taken into consideration. This is the total time for that step time. You say okay. Now we're going to make sure that because this is to be a 2D problem, none of these should be moving in the x direction. So let me do the following. Let me go ahead and under boundary condition to fix displacement, select all of these. I'm going to do this here. Yeah, all of these, all 10 of them. Yeah. And say, do not move in the direction x. Okay, good. So that makes it a two-dimensional problem. These two endpoints, and it's very important that you do not put the restraint or the boundary condition on the points, put it on the vertices. So this last one, this point, and that point, okay, do not also move in the direction y and z because these are pins, okay? So no displacement direction y and z. Now, rotations are not important because these are truss elements. And also at this load, at this point, we have a force of 600 Newton. So we go under load, force, this not point, I hit the point. This vertex basically, a minus 600 Newton. And then we say, okay, save everything. All right. And let's check it out first. Model and scenario check. And then the simulation check. Once this finishes, then we're going to go do the uh, actual simulation. I didn't ask for any specific uh, data to be stored because the default ones are going to do what we're looking for. Just a check. Good. And now the running the simulation. You can monitor it by clicking on this iterations tab. There is no iterations here, but it shows you the progress of the calculation. Going through. And I think it's finished right there. We're going to be looking at the deflection in just a minute. Okay, so close that. This is the initial step before things start to move. Then starts, things start moving. Okay. Now this is the von Mises stress, but let me change it to displacement. Biggest displacement obviously is going to be at the tip here. And one other thing, I want to I want to compare it with the results of this YouTube video. So I'm going to plot the displacement of this point as a function of time. Okay. So to do that, what I'm going to do is I'll go to uh, uh, right here, XY plot from history. You click on it. Okay. And I want the displacement. Uh, Model. I would have expected that the displacements to be actually stored here, but I don't see it. So what I'm going to do is now close this. Okay. So I will go back and uh, ask for that displacement. Okay. So unfortunately, I didn't do that. So let's go back to scenario and do two things. Go to you see that output? See that output? You click on it. I want uh, output for this point. Displacement. Now I don't need the force. So, and I needed history output. History output. Let me say OK. And unfortunately, we have to run it because I don't think you can still plot it here. Let's check. We go to uh, we go to results. Yeah, you see that you must resolve the problem. Close it. Okay, no problem. Gonna go and solve it. So we're not going to do the model check or scenario check. We're just going to run it and now look at the displacement of this point as a function of time. Ordinarily in dynamic analysis, displacement, I think the implicit displacement is automatically generated, but okay, so it's not here. So here is the iteration. So notice that there are two things that I did, several things that I did here that was unnecessary. One is to that meshing, I did it the long way. Then I didn't join it, etc. Then when I ran it, I forgot to ask for displacement, so I had to go back and ask for displacement and rerun it. It's going to be done. Extracting results. The contour plot doesn't matter here because yeah, there's no. Let's generate a plot. So we go to XY plot from XY plot from history. XY plot from history. I don't want translational acceleration. I want the displacement. Translation. Magnitude, for example, let's make it in the direction third component. There. So this is comparable with that. Okay. All right. Well, that's pretty much it.